Hi everyone, in this video we're looking at interval estimates or confidence intervals for means. So here's an example. We have a random survey of 40 Red Rocks Community College students, and these students reported a mean spending on out-of-pocket course materials like textbooks, access codes, etc. of $150. So that's the mean, with standard deviation $72. And this data is made up, but it's in line with national averages. We want to find a 95% confidence interval for the mean spending of all RRCC students. So we're looking at a scenario here where we have a sample and we're measuring the mean of our sample, this mean cost of books at $150. And we're trying to figure out what do we think the population mean is, or mu. Now, we won't know exactly what that is, but we can get a good estimate by taking 150 and giving us sort of an error, a plus or minus range around that 150 that should capture most likely the mean of the population. So the way we accomplish this uses the sampling distribution of sample means. So if I had some population and I'm sampling and then taking a mean, sampling, taking a mean, sampling, taking a mean, right, getting all of these sample means from many, many different samples, we get the sampling distribution of the sample means, which from the central limit theorem is a normal distribution. The center, or the mean of all of our sample means, is the mean from the population, so mu sub x bar equals mu. And the standard deviation of our sample means, the standard deviation of this distribution, is given by the standard deviation from the population, sigma, divided by root n. Now, we would like to use this, but there is sort of a problem with this construction, in that the standard deviation, or the standard error, which is the standard deviation of the sampling distribution, it depends upon a population value sigma, which we typically won't know if we're doing a sample and trying to estimate the population mean. So we're going to do we're going to use a slightly different distribution. And we're using this distribution called the student t distribution. This distribution looks a lot like the normal distribution. There's actually many different t distributions because it depends upon the sample size that you're dealing with. But it has a similar shape to the normal distribution. It has a central peak, it's symmetric on both sides, and it kind of tapers off on each end. The only difference is that this student t distribution will be a little bit shorter and more spread out. So something maybe like this. Particularly for small samples. So the smaller your sample size, the more kind of spread out, the fatter the tails of the distribution are. As your sample size gets very, very large, the t distribution becomes basically exactly the same as the normal distribution. So we're using this alternate distribution, and this alternate distribution allows us to use this standard error calculation where we're doing s divided by root n instead of sigma divided by root n. So because we typically don't know sigma, we don't know the population standard deviation, we use this alternate calculation, which is essentially estimating our standard error. And then we use the student t distribution to help kind of compensate for the error that's introduced by that approximation. So when we compute our interval estimate, we are going to take our sample mean to be the point estimate. So in this case, the point estimate is $150. That was the mean from our sample. And then we're going to use the standard error, this s divided by root n calculation. In our case, n was 40, that was the sample size, and s was $72, that was the standard deviation from the sample. We will always have sample standard deviation since we are collecting the sample data. In this case, that standard error comes out to about 11. And we're going to use that standard error to find a margin of error by adding and subtracting a certain amount from our point estimate. So I'm going to be calculating this in Excel. So I've created just some labels to help organize my information. I'm going to put X bar in here. That was 150. I have S, that was 72. N was 40. That's all information about my sample. Then the standard error, which I had on the screen there, the standard error would be the standard deviation. So I'm going to do an equal sign, click on my standard deviation S. That was the 72, divided by square root, so SQRT, parentheses, and then I'm taking the square root of 40. So you could just type those numbers in, or if you have them stored in cells, click on them like this, and this calculates out to 11.3842. The next thing I'm going to need to know is the critical value. So I went over the critical value in some depth in the interval estimates for proportions video, so you might check that out. In this case, we're using the same idea, but rather than getting a critical value of z star, which is essentially a z-score from the normal distribution, our critical value is t star, indicating that this is coming from the t distribution. This still represents the same thing. It's essentially a number of standard deviations that we're going to move away from our point estimate based on how much of the possible outcomes do we want to include. If you're doing this with Excel, when we found z star using a normal distribution, we used the norm.inverse function or something similar. With the t distribution, we can use this function t.inv.2t. The normal distribution, we had our mean and standard deviation for the standard normal, 0 and 1. And then this first input here that I'm calling p, this represented the area to the left. With the t.inverse.2t function, this first input also represents an area or a probability, but the .2t, that 2t stands for two tails. This input actually represents the area in both tails. So we'll look at an example in just a moment, and I'll show you what this looks like in terms of a graph, but these two functions do operate a little bit differently. So we're going to put in the area in both tails, and this is based on whatever confidence level we're looking at. And then the second input is the degrees of freedom. And for the purposes of this section, degrees of freedom, this is based on the sample size, is always going to be n minus 1. So sample size minus 1. Okay, so for this example, we wanted a 95% confidence interval. So we want to consider our t distribution, which again looks basically like a normal distribution. We're going to take, imagine taking the middle 95% or area 0.95, and we're kind of chopping off the tails of the distribution, an equal amount on both sides. And the critical value is the t-score, the t-value, the one on the right. There's also a critical value on the left, which is just the negative version of this t-star value. So I need to figure out what t-star would give us area in the middle, 0.95. So I will do this in Excel, but I'm going to be looking at the t.inv.2t function. The first input needs to be the area in the two tails. Now, if we have 0.95 area in the center, that leaves 1 minus 0.95 or 0.05, 5% area within both tails. Now, each individual tail would have area 2.5% or 0.025, but the two tails put together would be 5% here. So that's my first input. And then the second input, my degrees of freedom, is n minus 1. So the sample size for this example was 40. So this would be 40 minus 1, or I could just put in 39. So I'm going to be doing this for my t-star calculation. Here I have in Excel, so I'm doing equals t.inv.2t. You'll see Excel has the first input as probability. That is, again, that area in the two tails that we're trying to kind of chop off. And then degrees of freedom, I'm going to take my 40 and do minus 1. So whatever the sample size is, minus 1. So this gives me a critical value just a hair over 2. So we're going to use essentially 2 standard deviations or 2 standard errors above and below our point estimate. So here is the formula for an interval estimate for a mean. You should notice that this is fairly similar to what we had for a proportion. So we're starting with x bar, that is the point estimate, or the sample mean in this case, and we're trying to estimate, or we're coming up with an interval estimate for mu. So I have mu here in the center, and my upper and lower bounds of that interval estimate are x bar plus and minus the critical value times the standard error. So that is this expression that I'm highlighting in yellow, this t star times s over root n. So s over root n was the standard error. T star is the number of standard errors we want to use. That's our critical value. In this case, that was just over 2. So we're taking a multiple of the standard error and we're adding and subtracting this to x bar. So we can either write this as an inequality with my minus and my plus on the lower and upper bounds, or you could also write this as a single kind of plus or minus expression with the plus minus written here. So I've already got all my sample data. I've already computed the standard error. I've already computed the critical value. I can compute the margin of error here by taking my critical value times the standard error. And then for my interval estimate, I've left a little label or space here in the center for mu, and the lower bound would be equals, I'm going to take the x bar of $150 and subtract the margin of error. This margin of error would also be a dollar amount. And then for the upper bound, I'm going to take the x bar plus the margin of error. So on the low end, we get 126.97 or $126.97. And on the upper end, we get $173.03. So I could format both of these as dollar amounts if I wanted to, since they do represent dollars. You could also just do that manually. So this is an estimate of what we think the average student at RRCC is spending on textbooks and access codes and whatnot out of pocket for their courses. So between $127 and $173 approximately. This is giving us a range, and again, this isn't guaranteed to be correct because this is based on our random sample that saw an average of 150. And that 150 is likely fairly close to the population average or the population mean, but it also could be far off, right? Maybe we just got some randomness that created an extra large or extra small mean. But this, based on this sample data, this would be our 95% confidence interval. We're 95% confident that the true population mean is somewhere in this interval. If we did a different sample, we'd come up with a different interval. They almost certainly would overlap because of this range here. But 95% of the time when we do this, we will have captured the true population mean. That is it for this video. Thank you for watching.